Welcome back to The Explainer. Today, we're diving headfirst into one of the most mind-bending mysteries out there. What actually happens when our understanding of the universe just hits a brick wall? We love to think of physics as this set of unbreakable ironclad rules. But nature is really defined by its transitions. It's those extreme edges, like the exact second smooth water fractures into chaotic turbulence, or the frozen limits of space-time right near a black hole, where everything we think we know gets put to the absolute ultimate test. So what does it mean when physics just breaks? Imagine being a detective showing up to a crime scene only to find out that the laws of gravity and momentum have just been completely suspended. For decades, these weird boundary states have totally defied our standard mathematical formulas. When systems reach these extreme edges, our equations literally start spitting out nonsense. We get infinite values, utterly unresolvable data, or just pure chaos. But here's the exciting part. A recent wave of groundbreaking research, published in the summer of 2026, has finally begun to systematically dismantle these barriers. Okay, let's dive right into this. When scientists talk about a boundary problem, they're talking about that exact threshold where a perfectly orderly physical system just erupts into chaos, causing our traditional models to fail. But here's the real secret to how we're finally solving this. Researchers aren't just building bigger supercomputers to crunch more numbers. No. Instead, they are literally forcing next-generation AI and machine learning models to strictly obey the underlying symmetries and conservation laws of the universe. Think about the old way of doing things back in the 20th century. We relied almost entirely on raw data. If that data was noisy or incomplete right at the boundary, the model just got completely confused and crashed. But the new way, driven by these cutting-edge 2026 AI models, is a total paradigm shift. It uses physics-inspired architectures to essentially hard-code the rules of the universe right into the system. So, if the data gets noisy, the AI doesn't panic. It relies on its internal physical constraints to literally ignore the noise. All right, let's look at Section 1, the blindfolded tightrope walker, where we tackle autonomous navigation. I absolutely love this analogy from the researchers. Just imagine a blindfolded tightrope walker trying to carefully navigate a really unstable, windy platform. If they rely purely on the external shouts from the crowd, which in this case is our noisy data, one sudden distraction is going to make them fall. But if that walker relies entirely on their deeply ingrained internal sense of gravity and center of mass, they can completely tune out the noise. They reconstruct their path using only the physical, real sensations right under their feet. So, the crucial point is this. Traditionally, autonomous underwater vehicles completely rely on acoustic sensors to find their way around. But when you put them in deep marine trenches or under massive ice shelves, those signals get blocked or bounced around, basically feeding the drone garbage data. Enter a new AI framework called DVL DepotNet. Instead of just blindly trusting those faulty sensors, this neural network is already hard-coded with the physical equations of the submarine's own momentum and mass. It fundamentally knows what is physically possible and impossible for its own body to do, which lets it easily filter out all those acoustic illusions. And here's the kicker. By enforcing these physical consistency constraints, this system achieves a massive 40% improvement in navigation accuracy. 40%. That is huge. This isn't just some fun math trick. This directly unlocks our ability to explore the most extreme, totally unmapped underwater environments on Earth. Think deep marine caves and subglacial lakes using highly resilient, low-cost drones. Moving right along to Section 2, the impossible seating chart. Here we're looking at frustrated spin glasses. To wrap our heads around what a frustrated spin glass is, think of the ultimate wedding planner's nightmare. You've got guest A who absolutely must sit with guest B, but guest B flat out refuses to sit anywhere near guest C. Now imagine you have 4,096 of these highly opinionated guests to seat at a reception. In magnetic systems, these guests are individual atoms, and their magnetic spins just cannot satisfy all their alignment preferences at the same time. Traditional algorithms completely lose their minds trying to sort through the global drama of seating them one by one. So how do we fix this? Enter a brand new physics-inspired transformer. Standard AI models fail here because they try to look at everyone at the wedding all at once. But this new AI acts like an expert planner who realizes, hey, I only need to worry about the guests sitting immediately next to each other. By making the AI's internal structure mimic the actual geometric physical layout of the atoms, it completely cuts through all that computational noise. And the result? A massive 100x speedup in processing time. That is a real game changer. It means we can suddenly simulate these massive 4,096 spin systems on just a single standard graphics card. And why does this matter to you and me? Because these complex frustrated magnets are the exact foundational math we need to build next-generation quantum computers and ultra-dense magnetic storage drives. Next up, Section 3, Tipping the Heavy Refrigerator, Unraveling Turbulence in Pipe Flow. Let's shift gears back to fluid dynamics to tackle a mystery that has quite literally baffled scientists since 1883. We're talking about the exact moment smooth water flowing in a pipe suddenly becomes turbulent. Let's move to and see how this actually builds. Researchers have finally mapped out the exact physical steps that trigger chaos in a pipe. It breaks down into 3 phases. First, an initial or phase where the flow disturbances start to tilt. Then, a second phase where oblique waves collide with each other. And finally, a lift-up phase that creates these rapid high and low speed streaks, which ultimately fractures the smooth flow entirely. Now, to actually trigger this, think about tipping over a massive, incredibly heavy refrigerator. You don't just walk up and push it with brute force, right? Instead, you find a tiny wedge, slip it under a highly localized corner, and shake it at a very precise frequency. Fluid transition works exactly the same way. The optimal perturbation, the thing that ruins the smooth flow, isn't a massive wave. It's a tiny, minimal, highly localized seed of energy. And scientists have finally mathematically proven the threshold for that seed. It scales to the inverse cube of the Reynolds number. Basically, in plain English, the faster the fluid is moving, the less energy it takes to disrupt it and cause chaos. By finally understanding this math, engineers can now design ultra-precise textures for the insides of pipelines and the hulls of ships to suppress this exact trigger. We're talking about potentially saving billions of dollars in global energy costs just by keeping fluids flowing smoothly. Which brings us to Section 4, the library at the end, exploring planar Carroll systems. For our final boundary, we are traveling to the most extreme edge imaginable. We're talking about the event horizon of a black hole, where the speed of light mathematically drops to 0. Trying to calculate thermodynamics in this environment has historically just been a dead end. Imagine a library where patrons are strictly forbidden from moving or communicating at all. If literally no one can pass a message, how could the room possibly establish a uniform temperature or reach any sort of consensus? In a zero light speed environment, energy cannot travel. So how on earth does the system stabilize? And this brilliantly illustrates the solution. Researchers proved that if you take that entire totally silent library and place it on a rotating platform, the global rotation itself acts as a unifying physical clock. Even if the patrons can't move or speak to each other, the shared rotation of the room allows them to synchronize perfectly. Mathematically, they showed that in these bizarre zero light speed environments, global rotation is absolutely required to reach thermodynamic equilibrium. It's just an astonishing insight into how black holes actually function. Finally, Section 5, our new physical reality. As we step back from the edge of black holes and deep-sea trenches, what does all of this actually mean for us? It's super easy to get lost in all this abstract, high-level math. But let's bring it back down to Earth, because every single one of these discoveries translates directly into massive real-world impact. Cracking turbulence scaling, that means radically lower drag on global shipping and pipelines. Untangling spin glasses, that directly paves the way for faster, more powerful quantum computing. These new physics-aware AI systems are giving us resilient, deep-sea drones right now. And solving Carrel systems brings us one crucial step closer to a unified theory of quantum gravity. Now, what's really interesting about all of this is the true secret sauce of 2026. It isn't just about throwing more and more computing power at a problem. Honestly, it's about humility. It's about teaching our AI and our complex mathematical models to strictly enforce physical constraints, obey natural symmetry, and respect conservation laws. When we actually force our technology to play by the universe's own rules, the impossible suddenly becomes entirely possible. Which leaves us with one incredibly awe-inspiring question. We're clearly no longer just passively observing the boundaries of physics. We are out there actively decoding them. If we can hardcode the universe's own rules to solve its most chaotic extreme edges, what impossible barrier are we going to break next? Thank you so much for joining me on this explainer. Keep wondering, keep questioning, and I'll catch you next time.